Hello everyone, in section 1.2 we will learn some basic counting techniques, and these techniques are very important for throughout the whole semester. We'll try to learn them carefully and understand all of these techniques. The main topics in this section are tree diagram, multiplication principle, factorial notation, permutations, combinations, and finally distinguishable permutations. First, let's talk about the tree diagram. Tree diagram is a useful way to determine all possible outcomes of a sequence of experiments, provided that the numbers of possible outcomes for each experiment are not too large. So when we draw a tree diagram, it consists of a root, a number of branches representing for the outcomes of the experiments, and then possible additional branches, leaving the endpoints of other branches. It depends on how many experiments we have in the sequence of these experiments. The endpoints of the branches are called leaves, and they are used to represent the outcomes. So let's take a look at an example. We want to draw a tree diagram and determine the sample space in the experiment of tossing or flipping a coin consecutively 4 times. Again, we always have to assume that the coins always either land on head or tail. It doesn't land on the edge. So you can see here we start. This is the root right here. We start from the root. We have 2 branches coming out, and at the end of these 2 branches we will write head and tail, representing the possible outcomes for the first toss. Then for the second toss, again from each of the first head and tail, we have 2 branches coming out of those head and tail, representing for possible outcomes of the second toss. And we do again for the third toss and the fourth toss. And every time we have 2 possible outcomes. That means there are 2 branches coming out from the last endpoints. So based on this tree diagram, we can easily follow the branches and obtain the possible outcomes of this sequence of experiments. So if we follow this branch, for example, we have here head. First toss is head, the second toss also head, the third one is also head, and then the fourth one also head. So we have head, 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 head. If we go the last one, we go to the second branch, the tail one. Then we get head, 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 tail, and so on and so forth. So if we read all of these possible outcomes, then we obtain this sample space of this sequence of experiments. So that's how we draw a tree diagram. Let's take a look at another example. This time we have a bookstore wanting to stock t-shirts with different sizes. So here we can see there are 5 different sizes, and each size comes with 4 different colors: white, red, green, and black. Except size XL has only 3 colors: red, green, and black. And the XXL only comes in with green and black. We want to know how many t-shirts the bookstore has to display if the bookstore needs to display one t-search of a K. So again, this is a good case where tree diagram is useful because the numbers of possible outcomes for each experiment is not so large. In this case, we have here again the root, and first we will display the 5 different sizes represented by 5 different branches for small, medium, large, extra large, and XX large. And from each of these endpoints, we have other branches coming out representing for the colors of the t-search. So for size small, medium, and large, each of them have 4 branches coming out because they all come in with 4 different colors. While the XL has only 3 branches coming out, and the XXL has only 2 branches coming out. So from this we can see, we actually can easily count how many t-search the bookstores need to display. So we have 4 here, 4 here, 4 here, that's 12. 12 plus 3 is 15, and we have 2 more for the XXL, that's 17 total. Next we will talk about multiplication principle. This is a very important counting techniques, and I will present it in 2 different versions. Sometimes it's easier to use version 1 or match the problem with version 1, while in other cases it's easier to match with version 2. So in version 1, the situation is as follows. We need to perform a sequence of n tasks, and those tasks are denoted by t sub 1, t sub 2, all the way to t sub n. And suppose that there are k sub 1 different ways to perform task number 1, k sub 2 different ways to perform task number 2, and so on, and there are k sub n different ways to perform task t sub n. Then the multiplication principle says that there are totally k1 times k2 times k3 all the way to kn, all multiplied together, different ways to perform the sequence of tasks t1, t2, all the way to tn. And this result actually can be seen quite easily if you draw a tree diagram. And you can do this with small values of k1, k2, k3. It's easy to verify that. Let's take a look at an example. How many 8-digit case-sensitive passwords can be generated by using 26 alphabetic letters if the digits can be repeated? So think of this problem as a sequence of 8 different tasks you can do. But first let's talk about whether we can use tree diagrams here. The problem with that will be getting a huge tree diagram because it is sensitive passwords. And with 26 alphabetic letters, each of the digits can have 52 different choices. 52 different choices for each outcomes, for each digit mean that we have 52 branches coming out from the root, and then for each of the branch, the first branch, we have another 52 branches coming out. So this could be a huge diagram, and in this case it is a large tree diagram, and it's really not a good idea to draw the tree diagram in this case. However, we can treat this quite easily or solve this problem quite easily by using the multiplication principle in version 1, because we can treat this as a problem of performing 8 different tasks. With tasks, the first task is picking a letter for the first digit. The second task is to pick the second letter for pick a letter for the second digit, and so on until we fill in 8 digits. So there are totally 8 different tasks. For each of these tasks, there are 52 different ways to perform the task, because we have 52 different choices. So simply by using the multiplication principle, then we have 52 multiplied 52 8 times, which is 52 to the 8th. And if you use a calculator, you get this number. So that is the numbers of different ways to create a case-sensitive 8-digit password by using 26 alphabetical letters. Okay, now for the next example, it's similar. This time we want to see how many 5-digit zip codes can be created if we allow the digits to be repeated. So this is similar to the previous problem. This time, instead of 8 tasks as the previous problem, this time we have only 5 tasks, which are the tasks to pick the number for each digit. And for the first digit, we have a total of 10 possible ways, because we can pick a number ranging from 0 to 9. So we have 10 choices for the first digit. And since the digits can be repeated, the second digit we also have 10 choices. We also have 10 choices. The third digit, we also have 10 choices. The fourth one, we also have 10 choices. And the fifth one, we also have 10 choices. So the numbers of possible 5-digit zip codes when we allow the digits to be repeated will be 10 times 10 times 10 times 10 times 10, which is 10 to the 5th. And that's 100,000 different 5-digit zip codes we can create. In the next example, this time there is a restriction. That is, the first digit cannot be 0. So this time the only thing changed in this problem compared to the first one is on the first digit. This time, since we cannot use 0 for the first digit, there are only 9 choices when we pick a number for the first digit. The remaining 4 digits, we still have 10 choices. So the total possible 5 digits, the numbers of 5-digit zip code this time will be 9 times 10 times 10 times 10 times 10, which is 90,000. Okay. In example 6, we have a different kind of restriction. This time the digits are not allowed to repeat. So still the same question, how many 5-digit zip codes we can create with such restriction. So this time for the first digit, we have 10 choices. However, because we cannot repeat the digits already selected for the first digit on the second digit, so we only have 9 choices for the second digit. And then for the third digit, we are down to 8 choices. And then the fourth one, we only have 7 choices. And the fifth digit, we only have 6 choices. So this time, by using the multiplication principle, we have 32,040 different ways to create a 5-digit zip code. Now let's look at this license plate problem. The license plate has 6 digits, with the first 2 digits are capital letters, and the last 4 are digits. The question is how many license plates we can create with such rule. And we also assume that the letters and numbers can be repeated. So this is another typical examples where multiplication principle works nicely. So again, this basically, we have 6 tasks this time. For the first 2, for each of them we have 26 different choices. So that will be 26 times 26. And then for the last 4, each of them we have 10 choices. So that will be 10 times 10 times 10 times 10. And using the multiplication principle, we obtain 6,760,000 different license plates we can create with such rule. Now we look at another example. We have 4 friends taking a picture, and how many different ways we can arrange them. So think of this as first one is the 4 empty slots, and we need to fill in these slots. So we first have to fill in the first slot, and to do that we have 4 choices. Then for the second slot, we are down to 3 choices because there are only 3 people left to choose from. And then for the third slot, we have only 2 people left, so we have 2 choices. And finally, we fill in the last one. So this time we have 24 different ways to arrange the 4 friends for the picture. Now let's take a look at the second version of the multiplication principle. So this time there's a new terminology, that is the composite experiment. So what is composite experiment? So we have a sequence of n experiments, e sub 1, e sub 2, all the way to e sub n. They are performed in consecutive orders. Then that sequence of consecutive order is called a composite experiment, and we denote that composite experiment by just writing e sub 1, e sub 2, all the way to e sub n. So in the case we have a composite experiment, and for each experiment we have certain different outcomes. For example, we have K1 different outcomes for the first experiment, K sub 2 different outcomes for the second experiment, and so on. And K sub n different outcomes for the last experiment, the nth experiment. Then the composite experiment, that is a sequence of those experiments, has a total of K1 times K2 times K3 all the way to Kn outcomes. So this is the second version of the multiplication principle. Let's take a look at an example where we can apply this. So we have an experiment including first rolling a dice and then tossing a coin. We want to find all possible outcomes. So in this case, actually, you can also use a tree diagram, draw a tree diagram, and obtain the answer quite easily, because the number of outcomes for each experiment is small. But let's try to learn how to use the multiplication principle to solve this problem. So in this experiment, it is a composite experiment because it involves a sequence of two experiments. First, rolling a dice, and then tossing a coin. So it is clearly a composite experiment. And for the first experiment, rolling a dice, we have 6 possible outcomes. With the second experiment, tossing a coin or flipping a coin, we have 2 possible outcomes. So the total possible outcome for the composite experiment is 6 times 2 possible outcomes. Okay, next, let's learn the factorial notation. So this is just a notation which allows us to write things shorter to save the time. And this also looks neater. So what is a factorial notation? If we have a product of positive integers, and these integers are consecutive integers. You can see here we have n, then we reduce the next integer smaller than it is n minus 1. Then the one after the n minus 1 is n minus 2, 1 unit less. So if we keep doing this, eventually we will reach 1. So if we look at this product, if we have to write all the time, it's just time consuming. So to save a little bit on the writing, we will represent this product by what we call the factorial notation, which is written by n and then an exclamation mark. So the whole thing is read factorial, n factorial. And notice that for convenience, we also define 0 factorial is 1. Because in many formulas, that is how it works out well, without the need of adjusting the formula. So again, let's go through a few examples. 0 factorial, we know it is 1. 4 factorial, that is the product of 4, 3, 2, and 1, which is 24. The 10 factorial is the product of 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1, which is 3,628,800.